Okay, this video we're doing the third page of the Unit 8 review about volume and finding the area between curves, okay, using integrals and such. So here on question 12, we have the graph of 20 plus x squared minus x squared, which is probably this one, right, a negative quadratic. So we're going to call this one the F graph. So this is f of x. And then g is x squared minus 5x, which is probably the one below in this case. Okay, so it's pretty good to identify which graph is which, because when we're finding the area in between these two curves, it's always the top curve minus the bottom curve on the interval. Okay, well, I guess that means we need to figure out what the interval is also, don't we? So we need to figure out what are the x values where these two things intersect. Okay, so we do that by setting them equal to each other. 20, move it down. 20 plus x minus x squared equals x squared minus 5x. Okay, set the equations equal, and let's see if we can solve this for x. So let's get all of our x squareds on this. In fact, let's make our quadratic with everything on the right. Okay, let's just do that. So we have 0 on the left now, and I have 2x squareds, and I have minus 6x's and minus 20. Okay, so everything is on the right. I notice that I can divide all these things by 2, right? They're all even numbers. So let's simplify this even further by dividing everything by 2. So now I have a pretty factorable quadratic. This factors to x minus 5 and x plus 2. So my intercepts are positive 5 and negative 2. So this one here on the right will be the positive 5, and this one here on the left will be the negative 2. Okay, so those become your limits of integration. Right, negative 2 is the one on the bottom, and positive 5 is the one on the top. Okay, so then it's top function minus bottom function, which said was the f function was on top minus your g function on bottom. And since this is calculator active, you can just plug these two equations into your calculator. Okay, and I believe on the AP test, writing this out rather than plugging in your functions exactly would be perfectly fine. Right? They would know that you're doing the f function on top minus the g function on bottom, and whatever your calculator told you the answer was, that's going to be the answer. Okay, so let's see what that is. 343 divided by 3, which reduces to 114.333, repeating. Okay, so when we're finding the area of a curve, we have to figure out where they intersect, right? Because we have to have the left intersection point and the right intersection point. Okay, part B, a vertical line, x equals k, divide your region into two equal areas, right? But don't solve an equation that could be used to find the value of k. So we know that the area, right? So the integral from 0 to k, or from, I guess maybe not from 0, but rather from negative 2 to k, right, of whatever, that should be half of your area. Okay, so that's what the thought is here, is that we're taking the integral from negative 2 to k, right, some vertical line in here, some vertical line. So that means we're going to have a new, I don't know, maybe like this. Oh, I don't know, maybe that's not it. Right, so we're going to have a new interval. We're going to go from here to here, and that should be the area of half of your entire thing, right? Half of 343.3, since that's what the area of the whole entire thing was. Okay, so let's see, what can we do to make this look better? Negative 2 to k of your function, right? We had f of x minus g of x dx equals, maybe we just write 343 divided by 6, right? Because that's really when you multiply 343 thirds times 1/2, we get 343 sixths. So maybe that would be the best way to write it, right? Write but don't solve an equation. So from -2 to k, we have your left end point to some random x value, k, where your function's area is half of what it was up here. Okay, I think I like that. And then the third one, write but don't evaluate an integral expression for the volume when you're rotated around the line y equals -10. Okay, the horizontal line y equals -10. So let's come back up here and see where that would be. Okay, y equals -10 is somewhere way down here. Okay, so this is y equals -10. So we are rotating it, right? We have the same limits of integration. And we have two radiuses. We have the radius from our outer function, right, to your line of, or axis of symmetry, or axis of rotation, rather. Okay, and then we have the second radius, right? So we have the outer radius that creates the shell, and we have the inner radius that creates the open space, okay, of whatever this three-dimensional solid is going to look like. So the function farther from y equals -10, from -2 to 5, right, pi times, so it's a volume. So volume equals pi r squared. The farther radius is the f of x function minus -10 squared, right? F is the function that's farther away from your line. So it's the one that goes first, that creates the outer shell, minus the g function minus -10 also. Okay, so it's always minus the your axis of rotation. Okay, or you could write a +10. That would be sufficient if you wrote +10 in there also. F of x +10, because what's happening is your original y value, we are adding 10 units to that to make our radius, right? So whatever your original y value is for f of x, we're adding 10, and that's creating that circle that goes around your axis of symmetry, or rather axis of rotation. So once again, don't solve, just write it down, okay? So fairly okay stuff. Now number 13 has two different equations. Find the area of R. So once again, let's do a little sketch. Because being able to see what these graphs look like, we can tell which one is above and which one is below. Okay, because it's important to know which one's above and which one's below, and where they intersect. So y equals 2x, let's do that in blue. So it has a origin intercept, up 2 units, right 1 is the slope. Okay, so maybe we'll go up a couple of points. Right, so 1, 2, 3, 4, 5, 6. So here's the line y equals 2x. Also down to left 1, down to left 1. Right, because we want to graph enough so that we can actually see where these things intersect. So there's the graph of y equals 2x. So let's look at x squared minus 3. Okay, so that's our quadratic that's been moved down 3 units. So it has a -3 intercept, and you go 1 left and 1 up to find the quadratic, so 1 right and 1 up, and then 2 right and 4 up, and then 3 right and 9 up. So -3 plus 9 is 6, 1, 2, 3, 4, 5, 6. And we notice they intersect at nice pretty points, which makes me happy that we don't have to solve crazy things. Okay, so this is what the graph looks like, right? This is the graph of our function here, our two functions. Okay, so it looks like our interval that we're looking for goes from -1 to +3. Okay, so if we set these two equations equal to each other, we could make a quadratic and solve that and probably get -1 is +3 as your two x values that would solve this. So -1 to +3 is going to be your interval. So area is the interval from -1 to +3 of your top function, which was 2x, right? So we're looking from the top to the bottom. The top function is 2x minus the bottom function of x squared minus 3, and this is with relation to x. Okay, so we probably could do this without a calculator, but because it says calculator active, let's just use our calculator and figure out what that area is. Okay, so putting that into my calculator gives me the answer of 32/3 is your answer. Okay, so that's the area between these curves. That's what we found. Okay, part B, find the volume of the solid generated when R is rotated about the line y equals 8. Okay, so we have some horizontal line y equals 8 up here. Okay, so we want to have two radiuses, so our intervals are the same, but your first radius comes from the equation that is farther away from your axis of rotation. Okay, so this is your first radius. So volume equals pi times the interval from -1 to 3 of x squared minus 3 minus 8 squared, right? Because the area of a circle is pi r squared. So your radius is given to you by the function x squared minus 3 and then minus 8, because 8 is your axis of rotation. Okay, minus the second radius comes from the closer function. Okay, so this is your second radius, and that is 2x, also minus 8 squared, and then of course this is with respect to x. Okay, so some things that haven't changed are your limits of integration. We have multiplied it by pi, because that's what a circle is, pi r squared. So pi radius squared minus the closer radius squared. So once again, we're going to use our calculator here to figure this out.
For some reason it multiplied by
509.357 when you round to 3 decimal places. Okay, so that's kind of a lot, I guess, but it's a pretty big area that we're rotating by a long distance. Okay, part C, write but do not evaluate an integral expression for the volume when it's around the horizontal line y equals -5. Okay, so once again we have a vertical type of a rotation. So in this case, the integrals don't change from -1 to 3. But now, if we look at the line y equals -5, right, that line is down here. I guess this is -5. So your radiuses are going to change. The farther radius is going to be your blue line, right, or the 2x function. And your closer radius is going to be the red line, or the x squared minus 3 function. Okay, so we have y equals -5 as your axis of rotation. Okay, so the farther radius becomes the 2x minus -5, which is plus. So 2x plus 5 squared minus, let's see, what was it? It was x squared minus 3 minus 5. So in other words, that's going to be a minus 8 squared, and then of course dx. Okay, so it says write but don't evaluate. So that's really all we have to do, and it probably would have been fine if you wrote, oh, there's no f's and g's, so yeah, so you have to use your function because there's no f's and g's going on here. Minus a minus, sorry, this will be a plus 5. So we'd have a plus 2 in here if you were going to simplify before you put it into your calculator. Okay, so then the third one here is probably the most difficult one. Find the volume when it's rotated around the vertical line. Okay, so when we're rotating it around the vertical line, we have a horizontal rotation. And when you do a horizontal rotation, everything needs to be in terms of y. Okay, everything needs to be in terms of y. So this is going to be your new line of rotation here. Okay, so we have a horizontal rotation around that point. Okay, so the idea stays the same. We're going to take the farther radius, right, which is your 2x, once we solve it for y, minus the closer radius, which looks like it's your x squared minus 3. So we have to solve both of these equations for x real quick. That means x equals y over 2, and x equals the square root of y plus 3. Okay, square root y plus 3. Okay, so once again, your farther equation, we also need to have your integrals in terms of y. So the lower bound for your integral is negative 3, and your upper bound is positive 1, 2, 3, 4, 5, 6. So one of them intersected at negative 3, that's the lower bound, and the upper bound is positive 6. That is the integral that we are rotating, negative 3 to positive 6. So everything is in terms of y when you do a horizontal rotation. Okay, so I believe the blue one, which was y over 2 minus 5, right, it was x equals 5. X equals 4, right, x equals 4. So let's erase this and put a 4 there. Minus the square root of y plus 3 minus 4 squared, and then all this is in terms of y. Okay, and it wants us to find this, so we're going to plug this into our calculator with a dy, right? All of your variables are going to be y's. We have y-axis intervals, we have y equations, and let's see what that calculator tells me is the answer. 219.126. It's cubic units because it's volume. 219.126. So when you're doing any type of a horizontal rotation, okay, around a vertical line, everything has to be in terms of y. Right? Your limits of integration are in terms of y, your equations are in terms of y, and your d is in terms of y. Okay? So hopefully you can remember that and do awesome on your test.